Hi, everyone. Welcome to today's lecture on nuclear reactions. So previously, we talked about what radioactivity is, what a radioisotope is, and the four types of radioactive decay. Today, we're going to be looking at the specific nuclear reactions for each type of radioactive decay, and we're going to be talking about what happens to the nucleus of those radioisotopes. So our learning goal is to write a balanced nuclear equation showing mass numbers and atomic numbers for radioactive decay. The first thing we need to talk about is balancing nuclear equations. So here is an example of a balanced nuclear equation. Californium-251 decays into curium-247, and it gives off an alpha particle. And so what you need to be aware of is that the radioactive isotope, after it undergoes decay, can change both its atomic number and its mass number, which makes sense because it's spitting off a piece of its nucleus. And this is the piece that it spit off. The key thing to recognize is that the sum of the mass numbers and the sum of the atomic numbers are equal for the reactants and the products. So what that means here is if you're looking at the starting material, californium, it has a mass number of 251. There's something called the conservation of matter, right? We're not destroying matter. We're just taking it from one intact nucleus and we're breaking off a little piece of it. And the two remaining pieces have to have the same mass as the original piece. So the main nucleus became slightly smaller and its mass is now 247. And the piece that it spit off had a mass of 4. All right. And so 247 plus 4 is equal to 251, right? There was no loss in mass. The total mass is the same as the total mass. It's just separated into two different particles, which have the same mass as the original. And the same thing with the number of protons. So if you originally had 98 protons, we still have to have 98 protons. They're just in two different places now. And so the new nucleus has 96 and the alpha particle has 2. So 98 is equal to 96 plus 2. Right? So there's a conservation of mass numbers and there's a conservation of atomic numbers. So the number of protons doesn't change and the total number of protons and neutrons doesn't change. Let's look at alpha decay. So alpha decay is one of the more common types of radioactive decay. And that's when a radioisotope spits off an alpha particle. And so the mass number is going to be decreased by 4 because that's the total mass of an alpha particle. And the atomic number is decreased by 2 because there are 2 protons in the alpha particle. And so the uranium-238 is spitting off the alpha particle, and it's becoming thorium-234. So 238 is equal to 234 plus 4, and the number of protons, 92, is equal to 90 plus 2. And so to write this balanced reaction, it would look like this right here. This is what we call a balanced reaction for radiation decay, right? Your original radioactive isotope, the new element that it becomes, and the particle that it emitted, in this case, an alpha particle. So here's a quick guide to how to complete and balance these nuclear equations. First step is to write the incomplete nuclear equation. Second step is to determine the missing mass number, then determine the missing atomic number, then double check the periodic table to determine the symbol of the new nucleus, and then fill in the blanks to complete the reaction. Let's do an example. So here's the equation for alpha emission. And recall that this is the symbol for an alpha particle. So you have to have that memorized. Complete the following nuclear equation for the decay of americium-241. So americium has the symbol Am, and its mass number, they're telling you, is 241. Now, it is decaying, and it's spitting off an alpha particle. This is the symbol for an alpha particle. 4,2He plus something. And our goal is to figure out what this something is. Now, let's double check the periodic table to figure out how many protons are in americium. And down here we can see americium, and it has the atomic number of 95, which is how many protons are in it. So we'll go back and we'll fill in the 95 here. So let's take a look at mass. Originally, we had a total mass, Originally, we had a total mass of 241, and that's going to be equal to 4 plus what? So 241 minus 4 is going to be 237. So that's our new mass that's going to go up here. And then let's look at the proton number. Originally, we had 95. And so that's going to be equal to 2 plus what? So 95 minus 2 is 93. And so that's our new atomic number, 93. And so now that we know our mass number and our atomic number, we can go check the periodic table and figure out what element is number 93. So go back to the periodic table, and it looks like element 93 is neptunium, so NP. So we can go back here and erase our question mark and fill it in as neptunium. And so that is our balanced equation for alpha emission of americium-241. Okay. And the next 3 or 4 slides are just showing how to arrive at that, and it looks like we got the right answer. Let's talk about beta decay. So this is the symbol for a beta particle. Beta particle, remember, is just a high energy electron. And so it's a -1 charge and it has a mass of 0. So beta particles are emitted from a nucleus when a neutron breaks down to form a proton and a beta particle, which increases the atomic number by 1 because the neutron is becoming a proton. And so here, I don't know if you're looking closely enough, but you can see this white sphere is supposed to be the neutron. And then it has turned into a red sphere, which is supposed to be a proton. So this neutron became a proton, and in the process, it spit out an electron, also known as a beta particle. So the new nucleus is going to be nitrogen-14. So it was a carbon-14 because it had 6 protons, but this neutron became an extra proton. So now the proton number is 7, which is nitrogen. So the carbon became nitrogen and spit off an electron. The balanced equation for this look like this. Right? Our carbon-14 radioisotope underwent beta decay, become nitrogen-14, and it spit off a beta particle. Let's do a practice problem. Write an equation for the decay of potassium-42, a beta emitter. So we're going to start with potassium-42, and it is undergoing beta decay. And so beta decay spits off a beta particle. So let's write the symbol for the beta particle, 0, -1, plus something that we don't know. And our goal is to figure out what the new nucleus is. So we need to look at both mass and the number of protons. So let's start with the given here, potassium. Let's check the periodic table and take a look at potassium. And we see that potassium has an atomic number of 19, which means it has 19 protons. So we can come back and fill that in. And so our mass number, 42, has to be equal to the two masses of our beta particle and the new nucleus. And so the beta particle has a mass of 0. It's just an electron. And so 0 plus what equals 42? Obviously 42. So our mass number didn't change. Now for the protons, we have 19. And that has to equal -1 plus what? -1 plus what equals 19? 20. And so the atomic number, or the number of protons on our new nucleus, has to be 20. So now that we know the mass number and the atomic number, we go back to the periodic table and we look at what has an atomic number of 20. And we can see that calcium is element number 20. So we can erase our question mark and fill this in as calcium. And that is our balanced equation for the beta decay of potassium 42. And the next 3 slides here are just showing you how to solve it. And looks like we got the right answer. Let's do another one. Write the nuclear equation for the beta decay of cobalt-60. So key word here is beta decay. We're going to start with cobalt-60. It's beta decaying, which means it's going to give off a beta particle. And we know that the beta particle is an electron with a -1 and 0. And we don't know what the new nucleus is just yet. That's our goal, is to figure this out. So to the periodic table we go. We're looking at cobalt-60. So what's the atomic number of cobalt? And we can see cobalt is right here. So cobalt has 27 protons. Let's go back and we'll fill in atomic number as 27. We'll look at our mass and protons. So the mass initially was 60. That has to be equal to 0 plus 60. So our mass number didn't change. Number of protons, we started with 27 here. So the 27 has to be equal to the -1 plus what? So -1 plus what equals 27? Well, that's going to be 28. Okay. You can fill in the 28 there. Then we go back to the periodic table and we try to see what element has 28 protons. And we can see that nickel is the element with 28 protons. So we go back and erase that question mark. Now we know that it is, in fact, nickel. And that is the balanced equation for the beta decay of cobalt-60. So the next few slides are solving it. And it looks like, whoops, yeah, nickel 60. Looks like we got it right. Let's talk about positron emission. So positron emission has this symbol for a positron. And positron emission occurs when a proton is converted to a neutron and a positron. So protons, this is the symbol for a proton, becomes a neutron and it gives off the positron. And so here's a balanced equation showing positron decay. And you can see the mass number doesn't change, but the atomic number decreases by 1, okay? Because the proton became a neutron. Take a look at gamma radiation. So gamma rays have this symbol here. In gamma radiation, energy is emitted from an unstable nucleus, and the unstable nucleus is indicated by an italicized M following the mass number. And so right here, if you're looking at the technetium-99m, the M stands for like metastable, unstable, right? So this is radioactive. This version of technetium-99 is stable because it's emitted this high energy gamma ray. So with gamma decay, there's no change in the mass number or the proton number. It's just you go from an unstable high energy version of an isotope to a more stable version, and you give off the gamma ray. So balancing these, there's not really anything to balance. It's just the M goes away and you get the gamma ray. This table shows a summary of the different types of radiation. So I'm going to zoom it in so we can see it here. So here's the radiation source, the type of radiation emitted, and what the new nucleus looks like. So for alpha emitters, they emit the alpha particle, which has this symbol. And so the new element has a mass number that is 4 lower than the original, and the atomic number is 2 lower than the original. Beta emitters emit a high energy electron or a beta particle. So the new element has the same mass number, but the atomic number is increased by 1. Positron emitters emit positrons, which have this symbol. So the new element has the same mass number, but the atomic number has decreased by 1. And then gamma emitters emit gamma rays, and the stable version of the element has the same mass number and the same atomic number. So how can we produce radioactive isotopes? We said a lot of them are naturally occurring, which is true, but some of them are not naturally occurring and they are synthetically produced in labs. And we can produce them by bombarding stable nuclei with particles. And so this process is called transmutation because we are mutating one element into a new element. Transmutation. This particular reaction is showing the stable boron 10 nucleus being bombarded with an alpha particle. And when the alpha particle hits it, some of it sticks and it becomes a larger nucleus, and one of the nuclei gets thrown off. So this is kind of like in pool when when you break and the cue ball hits and then something else comes off, right? We're hitting the boron with a alpha particle, some of it sticks, and we're spitting off one neutron. And so the boron is now nitrogen-13, which is radioactive, and then this will continue to decay again until it becomes stable. So let's look at the equation for producing new isotopes by bombardment. Write the balanced nuclear equation for the bombardment of nickel-58 by a proton, which has this symbol, which produces a radioactive isotope and an alpha particle. So they're telling us that we are using a proton to hit nickel 58, and it's going to produce arrow a radioactive isotope, which we don't know what that is, and an alpha particle. And so an alpha particle has this symbol. And so we want to fill in the blanks here to complete this balanced reaction. So let's start with nickel. They tell us that the mass number is 58. We need to go to the periodic table, look at nickel, and we see that nickel has an atomic number of 28. So let's go back in and fill in the 28 there. Now, we're looking at mass. Remember, both sides of the equation have to be equal. And so the mass of this proton is 1. And the mass of the nickel is 58. So 1 plus 58 has to equal something plus 4. So 1 plus 58 equals what plus 4? Well, that's going to be 55. We can fill that in there. So 55 plus 4 is 59. 1 plus 58 is 59. We're good. So we know that the mass up here has to be 55. Now let's look at the protons. The single proton has an atomic number of 1. Nickel originally had 28 protons. And so that has to be equal to something plus 2. So 29 equals something plus 2. That's going to be 27. All right. 27 plus 2 is 29. 28 plus 1 is 29. So we can fill in 27 for the atomic number of our unknown nucleus. And the last thing we do is we go back to the periodic table and we figure out which element is number 27. And it looks like cobalt is element number 27. We can go back in and we can fill in this question mark as cobalt. And that is our balanced equation for this bombardment. Okay. So these next few slides are just showing us solving like we did together. And let's see, we got cobalt 55, and looks like we did it right. Let's do another practice problem. What radioactive isotope is produced when a neutron bombards technetium-99, releasing an alpha particle? So we are taking a neutron. And what's the symbol for a neutron? Well, that's N with a mass number of 1 and an atomic number of 0. And we are bombarding technetium-98, which is going to release an alpha particle. So 4,2He and some unknown new nucleus, which is what we're trying to figure out. So first thing, let's take a look at technetium and figure out how many protons there are. So technetium is Tc. Oh, where is it? There we go. So technetium has 43 protons. So let's go back in and we'll fill in the 43. Now, let's take a look at mass. So we know that the reactant side has to equal the product side. So 1 plus 98 has to equal 4 plus what? So 99 minus 4 is going to be 95. We can fill in the mass number as 95. Then we'll look at the proton. number. And so 0 plus 43 has to be equal to 2 plus what? So 43 minus 2 is going to be 41. Now, this has to have an atomic number of 41. So what do we do next? Back to the periodic table, and we try to figure out what the element is that has atomic number of 41, and that is niobium, Nb 41. And that completes our balanced reaction when technetium-98 is bombarded with a neutron to emit an alpha particle, and it decays into niobium. And so these next couple slides are just solving what we just did together here. So let's double check our answer. Should be Nb95. Oh, looks like we did it right. So that concludes our lecture today on balancing nuclear reactions. Thanks for watching, and I'll see you in the next video.